Next, we see that BPC is the sum of angles BPD and CPD. And because of the fact that BPD and CPD are inscribed angles, they are each equivalent to 1/2 of angle BO1D and angle CO2D, respectively. And then we can substitute the values of angles BO1D and angle CO2D from these equations here, and then we get 1/2 times the quantity angle ABD plus ADB plus ADC plus ACD. And because of the fact that ABD and ADB are basically two of the three angles of triangle ABD, and ADC and ACD are two angles of triangle ADC, we can make the following substitution. So ABD plus ADB is equal to 180 minus angle BAD. And ADC plus ACD is equal to 180 minus CAD. And then that gives us 1/2 times the quantity, 360, minus angle BAC. From the beginning of the problem, we found out that BAC is equal to 60 degrees. So making that substitution here gives us the value of angle BPC as 150 degrees. Now, the next thing we want to do is let BP equal A and let CP equal B. The reason for this is because we want to form equations that we can use to find the maximum possible area of triangle BPC, which is our one of our goals stated in the original problem statement. And we see that the area of BPC can be expressed as half AB sine 150 degrees, or 1/4 times AB. From the law of cosines in triangle BPC, we see that BC squared is equal to A squared plus B squared minus 2AB cosine 150 degrees. That means 14 squared, or 196, is equal to A squared plus B squared minus 2AB times -√3/2, or A squared plus B squared plus √3 times AB. So we want to maximize the quantity 1/4 AB under the constraint that A squared plus B squared plus √3 times AB equals 196. Well, for those of you fans who know multivariable calculus really well, or really admire Max Schindler, you would go about using the method known as Lagrange multipliers. And Lagrange multipliers help us to optimize multivariable functions that have two or more variables in them. You have to maximize or minimize a certain function given a certain constraint, and then you would use the method of Lagrange multipliers. So how do we do this? Well, first of all, let's look at the function that we have to maximize, which is BPC area equal to 1/4 AB. And we have to find the gradient of that. So we have to take the derivative of area of BPC with respect to A. That gives us 1/4 B. And with respect to B, 1/4 A. This gradient is equal to the Lagrange multiplier times the gradient of the constraint function with respect to A, which is 2A plus √3 times B, and then the derivative of the constraint function with respect to B, which is 2B plus √3 times A. So given these two, this gradient equation, we have Lagrange multiplier equal to 1/4 B divided by 2A plus √3 times B which also is equal to 1/4 a divided by 2b plus root 3 times a. The 1/4 we can cancel out the 1/4 and then cross multiply to get 2b squared plus root 3 ab equal to 2a squared plus root 3 ab. Cancel these out, cancel out the 2's. We got b squared equals to a squared, or b equal to a. So we get to maximize the area when a is congruent to b. And so that basically means that we need to have 196 equal to a squared plus root 3a squared. So a squared is equal to 196 divided by 2 plus root 3, or 196 times the quantity 2 minus root 3, formed by rationalizing the denominator, because 2 plus root 3 times 2 minus root 3 is equal to 4 minus 3, or 1, via difference of two squares. So we have a squared equal to 196 times the quantity 2 minus root 3. Now, looking back at this equation, we see that the area of BPC is equal to 1/4 AB. And that is the same thing as 1/4 A squared. And plugging this in and simplifying gives us the area of BPC equal to 49 times the quantity 2 minus root 3, which is in A minus B root C form, 98 minus 49 root 3. So A plus B plus C is equal to 98 plus 49 plus 3, which yields our final answer of 150.